Today we want to present our DualScope 95 scanner, which is here in a setup with a small granite stage. Here in the middle you have the DS9550 scanner. On top of it you see a CCD camera which is able to look through the scanner right at the spot where the AFM tip interacts with the sample surface. The grey granite arrangement around it is the so-called compact stage. To insert a cantilever, we lift out the scanner CCD camera arrangement. We use our unique plug-and-play system for cantilevers to insert the cantilever into the scanner. The next step is to place a sample. In this case we use HOPG on a small wafer. We reinsert the scanner and focus the sample surface with the set adjustment screw. Now we can see the CCD image that we can have the right distance to the sample so that we can focus the sample. Now we are looking for a rather clean spot on the sample so that we can perform our measurement. The next step is to make a sensor setup. We are running AC mode in this measurement, so we want to find the resonance frequency of the cantilever. This is done by hitting the full sweep button. The system will search and identify the right resonance frequency totally automatically. If the system gives us the OK sign on the left side, we can confirm this by hitting the OK on the right. Next step is to approach the sample to start with the measurement. You can see that the cantilever is now also getting close to the focal plane. Now the AFM has reached the surface and we can see that it's making an image of our sample. You can see the typical layer structure of the HOPG. And we also can see that when I speak you see some noise. I will now stop speaking to get a nice image. We can see that the image we recorded last doesn't have the noise in some of the lines, so we can use this image for analyzing the step heights of the HOPG. Down here in the graph we can now measure the heights of the steps I have marked here with the profile tool in the image. Here we can see that there's a 1 nanometer step, but the lower step should be even smaller. We can see that it's around 600 or 700 picometer. That means that in the lower step we have 2 atomic layers over each other, which corresponds to the more or less 700 picometers we observe in the measurement. The next sample I want to measure is a more daily life sample and should also show the flexibility of this setup. For the next measurement, we want to use an iPhone display to see how flat and how the structure of this surface looks like. Therefore, I remove the sample from the sample stage. I remove our little adapter here, and then I place the iPhone as it is on the sample stage. Then I have to adjust for the additional height of the iPhone, because this sample is just thicker. Then I will put in the scanner again, and also adjust again for the height to focus the surface of the sample. So this should be it. Then I lock the system again to have a firm connection between the scanner arrangement and the sample. Then I will also use the again the approach to get the AFM tip close to the surface. Now the AFM has reached the surface again, and we can see that it's now imaging the display of the iPhone, and the structure appears on this. We can also present this data in 3D. You can see how the image builds up in 3D. You can see that we can see some holes on the surface and also some scratches. These are most probably defects which occur in daily use of the iPhone. These are not big damages to the surface. If we use the measuring tool again, we can see that here we are also talking about nanometer deep scratches and defects on the surface. You can see that here. This, for example, this largest scratch on the surface is 10 nanometer deep and has a width of around 200 nanometers. This is very, very small. Compared to our HOPG sample, we can see that the height difference on the iPhone, because of the scratches, is just twice as much as on the very flat, atomically flat in some areas, HOPG samples. And this shows that also samples or surfaces in our daily life can be very flat